Thanks for introduction. Hello everyone, I'm Jiayan from Beihang University, Beijing, China. Our paper is Efficient Flower Text Entry in Virtual Reality. This work is together with Lili Wang, Xiaolong Liu, Xuehai Shi, and Miao Wang from Beihang University. Text entry is an important task for many virtual reality applications. Controller-based methods are now commonly used. However, their typing speed and accuracy still need to be improved. Here are the state-of-the-art controller-based methods for text entry in VR. Pizza Text divides a circular keyboard into several pizza blocks and uses a dual joystick controller to make two-step selections. Controller pointing is a common method in consumer VR systems. Hi-pad is a single-hand technique using one controller with a touchpad. The Google Drum keys uses the rays emitted from the controllers as a drumstick and taps down on the keyboard for selection. We think that the single-hand method is easier to learn and frees one hand to do other tasks, so we focus on single-hand techniques, and some of the existing methods require special controllers such as joysticks and touchpad, and we want to use the most common controller with only a few buttons. The circular keyboard layout is often used in text entry techniques. They often divide the 26 letters in a circular range of areas for selection. We also take advantage of the circular layout in our design. We explore design rationales from the following three aspects. First, we want to take advantage of the user's familiarity with the QWERTY keyboard, and we retained the three-row design and the order of the letters in each row and the left and right-handed keyboard zooms. We also provided keystroke sounds similar to hitting a real keyboard. And the second one is the interactive process of physical keyboards can be transferred to virtual reality. We can use the 3D hand translation to move the controller to find the target key on a virtual keyboard and then select it with a single keystroke. And some visual, auditory, and haptic-related aids can help users confirm which key they are selecting and whether the key has been selected. Finally, word prediction and error correction functions can improve accuracy, and human perceptions of the distance of the hand motion are non-uniform. This factor should be also taken into account. We combine the QWERTY layout with the circular layout. We first divide the QWERTY layout into 6 parts, rotate the top 2 parts up, rotate the bottom 2 parts down, and place the space key between the middle 2 parts. The layout is like a blooming flower, which is where the name of our method comes from. In terms of the interaction design, first we should place the keyboard in a certain position. We call it a reset. We attach the function to one button on the controller, and when we press the button, the controller's current position is bound to the origin of the coordinate system, which is also the center of the keyboard, with the user's head facing forward as the negative direction of the z-axis to create the coordinate system. Then we should map our head translation to the keyboard. In the left video, O is the origin of the system, P represents the position of the controller. We project the vector OP into XO plane to get the vector OP prime, which indicates the translation direction, and the Euclidean norm of the vector OP indicates the translation distance. We use a linear mapping function to map the translation distance to the keyboard, and use the translation direction directly. There is another functional key on the controller. We will introduce it later. We evaluate the user's typing speed with the metric of words per minute, and we evaluate the accuracy of typing with the metrics of not corrected error rate and total error rate. The workload is evaluated with the metric of NASA TLX questionnaire scores. In the pilot user study 1, we proposed 2 types of letter layouts and 4 possible optimization options according to the design rationales and evaluated them. QWERTY layout is familiar to us, and some other methods also use an alphabetical order layout. The default keyboard color is gray. Another possible option is highlighting the keys in different colors. We use 3 colors according to the letter frequency in English. Single color makes each key difficult to distinguish, and multiple bright colors can enhance the user's distinction between keys. The default method only has the visual feedback that the candidate key will be enlarged slightly, while the exact hand position hint may help the users select quickly, which is a continuous visualization rather than discrete. Word prediction and correction can predict the subsequent letters in the word based on the letters that the user has entered to perform word completion, which can also automatically correct spelling errors. We provide two candidate words, and users can use the functional button on the controller to select them. We also consider providing a sound similar to typing on the physical keyboard, and also a window-style delete sound. Tactile feedback refers to the vibration of the controller when switching candidate keys. We recruited 18 participants, and we use a within-group experimental design in which each individual was required to complete 10 sessions. The experimental results showed that the QWERTY layout and all the optimization options significantly improved the typing speed and reduced the workload. In terms of accuracy, there was no significant difference between optimization options and the default setting in NCER and TER. In pilot user study 2, we explored the effect of the mapping function on typing performance. We've formulated two hypotheses. Different mapping coefficients would affect users' typing performance. Optimizing the distance mapping process could improve typing speed and reduce error rate. In pilot user study 1, we found many misselection phenomena. We believe this may be caused by unreasonable mapping functions, so we first chose 5 sequentially increasing coefficients for the experiments. We found when k equals 4.5, the typing speed was the highest and the error rate was the lowest. At the same time, we collect their click points. These points include some misselection points. We believe that such data can reflect the distance perception habit of users. We use this equation to convert the collected 3D points to 2D plane to visualize them. Then we analyzed the distribution of the click points of k equals 4.5. We found that the center of the keyboard was off the intent position 0,0. Therefore, we recalculated the mapping coefficients of each key using this function. The len means the distance between the center of the keyboard and the center of each key in unity. We regard right horizontal direction as the direction 1. Direction 2 to 6 are other 5 directions in counterwise order. Key 1 to 4 are keys arranged from the center to the outside in each direction. We do not use the date of the last key in each direction because the hand translation may be exaggerated when the user selects them. Interestingly, the key value of the keys around the center of the keyboard were all less than 4.5, while the key value of the keys outside this range were all greater than or equal to 4.5. This shows that the user's perception of hand translation differs between the area near the center and the area far from the center. Hence, maybe a piecewise linear mapping is more appropriate. Experimental results show that the typing performance of the first 5 sessions had an increasing and then decreasing trend, and the piecewise mapping improved typing speed significantly and reduced error rates compared to setting the k value with a constant value for all directions. This supports the two hypotheses we proposed. Therefore, we choose the piecewise mapping as the mapping function of our method. We conducted a 6-day user study to evaluate the performance of flower text entry. We recruited 10 participants. 5 of them were from pilot user studies, 5 were newly recruited. In the last day, the typing speed of the novice group reached 17.65 WPM, increased by 96.99%. and the typing speed of the potential expert group reached 22.97 WPM, increased by 23.56%. The highest typing speed was up to 30.80 WPM, achieved by a potential expert participant in the sixth day. In terms of accuracy, both the NCER and TR were low. We proposed flower text entry, which is a new flower-shaped keyboard and a single-hand method with only a simple controller. We introduced 3D hand translation interaction into controller-based text entry techniques. Our method is efficient, accurate, and easy to learn for users and can be easily integrated into the existing VR systems. There are some limitations of our method. It requires a certain amount of physical space to use, and a very crowded environment may influence its performance. It cannot be used directly for the user's state when moving. The arranging of the interaction coordinate system should be modified, which may affect the typing experience. It cannot be used while the user's hands are occupied or in a VR system without controllers. In the future, we will improve our method from the following four aspects. To adapt our method to mobile sceneries, we can adaptively provide an appropriate arranging of interactive coordinate system. To explore if more hand motion can be integrated into text entry and improve keyboard design with more hand motion features. To explore whether using our keyboard in a crowded virtual scene would affect the efficiency of text entry. To find the relationship between color map and letter frequency according to the characteristics of human visual system, so as to better visualize our keyboard. That's all. Thank you for your attention.